Number 1, part A. Sketch the graph represented by the equation 9x squared plus 4z squared equal to 36. In this equation, we can see that it only contains x and z. The y component is missing. If the y component is missing, this graph is a cylindrical surface, and it's perpendicular to the xz plane. Since it only contains x and z component, it's a cylindrical surface perpendicular to the xz plane. Let's first of all draw the cross section in the xz plane first. In the xz plane, we have 9x squared plus 4z squared equal to 36. This is an ellipse in the xz plane. If I substitute 0 for x, 4z squared is 36, z squared is 9, z equal to plus or minus 3. So the intersection in the z-axis is positive and negative 3. If I let z equal to 0, I have 9x squared equal to 36, which means x squared equal to 4. So x equal to plus or minus 2. So the intersection in the x-axis is positive and negative 2. Next, let's draw an ellipse in the xz plane. That's the cross section in the xz plane, which is an ellipse. Here, the s-intercept is 2 and negative 2. Z-intercept is positive 3 and negative 3. And since this equation doesn't depend on y, when y equal to 1, the graph is the same. When y equal to 1, the graph is the same. When y equal to negative 1, the graph is also the same. Then connect this cross section. By connecting this cross section, we get a cylindrical surface. By connecting this cross section, we get a cylindrical surface. That's a graph of the cylindrical surface. It's perpendicular to the xz plane and passing through the ellipse, passing through the cross section in the xz plane. Passing through the ellipse, which is a cross section in the xz plane. Number 1, part B. We try to sketch the graph for this equation. First of all, let's pick some different values for z and look at the level curve along z-axis. When z is 0, if I plug in 0 for z, I have 4x squared minus 9y squared equal to 0. Then solve the equation for x or y. I have 4x squared equal to 9y squared. Divide both sides by 9. I have 4 over 9x squared equal to y squared. If I take square root, I get plus minus 2 over 3x. This equation represents two lines. This equation represents two lines in the xy plane. In the xy plane, this equation represents two lines. Y equal to 2 over 3x is a straight line passing through the origin. Y equal to negative 2 over 3 is another straight line passing through the origin. That's when z, that's the level curve when z equal to 0. When z equal to 1, this equation can be rewritten as, when z equal to 1, this equation can be rewritten as 4x squared minus 9y squared equal to 1. That's a hyperbola. That's a hyperbola. Hyperbola has two types. One type open up and down. Another type open left and right. Which type is this? If I substitute 0 for x, I can see that if I substitute 0 for x, there's no solution for negative 9y squared equal to 1. So that means this curve won't touch y-axis. But if I substitute 0 for y, I have 4x squared equal to 1. If I substitute 0 for y, I have 4x squared equal to 1. So x-intercept will be positive negative half. X-intercept is positive negative half. That's the level curve. That's the level curve when z equal to 1. When z equal to 2, we have 4x squared minus 9y squared equal to 2. So same thing, if I plug in 0 for y, x squared, if I plug in 0 for y, x squared is sub for x squared, I get a half. So x squared, if I substitute 0 for y, x squared is half. X is plus minus 1 over radical 2. 1 over radical 2 is more than a half. So it's further away from the origin. So we see the pattern. As z increase, the curve moves further away from origin. But z could also be negative values. Let's look at some negative z value. When z is negative 1, I have 4x squared minus 9y squared equal to negative 1. That can be rewritten as 9y squared plus 9y squared minus 4x squared equal to 1. If I substitute 0 for y, there's no solution for x. That means the curve won't touch x-axis. But if I substitute 0 for x, y is positive negative 1/3. So it passes through 1/3 in the y-axis. It passes positive negative 1/3 in the y-axis. When z is negative 2, we have 4x squared minus 9y squared equal to negative 2. That can be rewritten as 9y squared minus 4x squared equal to 2. Then if I substitute 0 for x, y squared is 2 over 9. Y is plus minus radical 2 over 3, which is further away from origin. This point is 1/3. This is radical 2 over 3, so it's further away from the origin. So we see that as z become larger negative number, the curve move away from the origin. So that's the level curve. Next, based on the level curve, Let's try to draw a 3D picture. Based on the level curve, let's try to draw a 3D graph. So when z is positive, we have hyperbola open in x direction. When z is positive, we have hyperbola open in x direction. When z is positive, we have hyperbola open in x direction. When z is negative, we have hyperbola open in y direction. When z is negative, we have hyperbola open in y direction. When z is negative. When z is negative, we have hyperbola open in y direction. That's how the 3D shape looks like. Now, let's look at the intersection. Let's look at the intersection in xz plane and yz plane. Let's look at the intersection in xz plane and yz plane. In the xz plane, we set y equal to 0. In the yz plane, we set y equal to 0. If I set y equal to 0, I have 4x squared equal to z. Then 4x squared equal to z. That's a hyperbola open. That's a parabola open upward. That's a parabola open upward. That's a parabola open upward in xz plane. That's a parabola open upward in xz plane. In the yz plane, we set s equal to 0. If I set s equal to 0, I have negative 9y squared equal to z. That's a parabola open downward. 9y squared equal to z, that's a parabola open downward in yz plane. So we have a parabola open downward in the yz plane. That's the 3D graph. It looks like a horse saddle. Then next, let's add the axis here. That's z-axis going upward. X-axis. It's x-axis. That's the y-axis. Number 1, part C. Sketch the graph represented by the equation x squared minus 4y squared minus 4z squared equal to 1. In this equation, we can see that both y and z has negative coefficient and x has positive coefficient. So we can move x squared over. If I move x squared over, I have negative x squared plus 1. Then in order to make the coefficient positive, I can multiply both sides by negative 1. I have 4y squared plus 4z squared equal to s squared minus 1. Next, we can pick different value for x and look at the level curves. Next, we can pick different value for x and look at the level curves. When s is 0, we have 4y squared plus 4z squared equal to -1. Since the sum of perfect squares cannot be negative, so there's no solution for y and z. That means there's no image when x is 0. There's no images. There's no image when s is 0. When s equal to positive or -1, since we have x squared here, when I plug in positive -1, the value is the same. When s is positive or -1, we have 4y squared plus 4z squared equal to 0. Since 4y squared is non-negative, 4z squared is also non-negative. If their sum is 0, that means they must both be 0. So we have y equal to 0 and z equal to 0. So when s is positive -1, we have y equal to 0, z equal to 0. The level curve here is 2 points. 1, 0, 0, and -1, 0, 0. When s is positive or -2, we have 4y squared plus 4z squared equal to 2 squared is 4. 4 minus 1 is 3. This is a circle. 4y squared plus 4z squared equals 3. This is a circle. Center and origin. Radius is square root of 4 over 3. So when s is positive or -2, the graph is a circle. Radius is square root of 3 over 4, which is square root of 3 over 2. Where s is positive or -2. When x is positive or -3, we have 4y squared plus 4z squared equal to 3 squared is 9. 9 minus 1 is 8. If I divide both sides by 4, y squared plus z squared equal to 2. That's a circle. Radius is square root of 2. And this is a little larger. Here we can see that as s increases, the circle gets larger. As s increases, the circle gets larger. So let's draw the 3D graph. When s is 0, there's no image. When s is positive or -1, we have 2 points. When s is positive or -1, we have 2 points. When s is positive 2 or -2, we have a circle, radius vertical 3 over 2. When s is positive 3 and negative 3, we have a larger circle. Next, let's look at a cross-section in the SY plane and XZ plane. For cross-section in the SY plane, we set Z equal to 0. For cross-section in the SY plane, set Z equal to 0. If I set Z equal to 0, I have x squared minus 4y squared equal to 1. S squared minus 4y squared equal to 1. This is a hyperbola. This is a hyperbola in the SY plane. If I set s equal to 0, there's no solution for y. If I set y equal to 0, s is positive and negative 1. So the graph is hyperbola in the SY plane. If I set y equal to 0, I have x squared minus 4z squared equal to 1. So in XZ plane, I also have a hyperbola. So the cross section in SY plane, and XZ plane are both hyperbolas. So the cross section in the SY plane is a hyperbola. The cross section in the XZ plane is also hyperbola. It looks like this. That's the cross section in the XZ plane. Number 1, part D. We try to sketch the graph for this equation. First of all, let's observe this equation first. We have s squared, y squared, z squared. Coefficient of x and z here are positive. Coefficient of y squared is negative. So I can move 4y squared over, make this term positive. So this equation can be rewritten as s squared plus 4z squared equal to y plus 4y squared. Next, we can pick different values for y and find the level curves along the y-axis. When y is 0, we have s squared plus 4z squared equal to 1. That's an ellipse. This is an ellipse. Let's draw this ellipse. Let's draw this ellipse in XZ plane. If I substitute 0 for x, I have 4z squared equal to 1. solve an equation for z equal to positive negative a half. If I substitute 0 for z, I can solve for x equal to positive negative 1. So this graph is an ellipse. That's the level curve when y equal to 0. When y equal to 1, I have s squared plus 4z squared equal to 5. When y equal to 1, I have 5 on the right side. These two ellipses have the same shape, but this one is larger. And since we take square for y, no matter what I plug in positive 1 or negative 1, I get the same level curve. I plug in positive 1 or negative 1, I get the same level curve. When y equal to positive negative 2, I have s squared plus 4z squared equal to 17. If I plug in 2 for y, I have 17 on the right side. This is a much larger ellipse. This is a much larger ellipse when y equal positive negative 2. So we see that as y increase, the ellipse gets larger. As y increase, the ellipse gets larger. Next, let's look at level curve in the xy plane and yz plane. Let's look at intersection in the xy plane and yz plane. In the xy plane, we set z equal to 0. In the xy plane, we set z equal to 0. If I substitute 0 for z, I have 1. If I substitute 0 for z, I have s squared minus 4y squared equal to 1. This graph is a hyperbola. In the yz plane, we set x equal to 0. If I substitute 0 for x, I have negative 4y squared plus 4z squared equal to 1, which can be rewritten as 4z squared minus 4y squared equal to 1, which is also a hyperbola. So let's draw a 3D graph. Based on this information, let's draw a 3D graph. When y equal to 0, the graph is an ellipse. That's the inner one, the inner ellipse. Next, when y equal to positive negative 1, we have a larger ellipse. When y equal to positive negative 1, we have a larger ellipse. When y equal to positive negative 2, we have a much larger ellipse. When y equal to positive negative 2, we have much larger ellipse. In the YZ plane, we have a hyperbola. In the YZ plane, the cross section is a hyperbola. In the SY plane, the cross section is also hyperbola. That's the 3D graph. Next, let's draw the axis. That's the origin. That's the y-axis. Y-axis on the other side. X-axis. X-axis on the other side. Then the Z-axis. So that's the 3D graph. Number 2, part A. Show that dt over ds equal to k times n. So let's try to prove it. Let's prove it. dt over ds using chain rule. It can be rewritten as dt over dt over ds over dt. The numerator dt over dt can be rewritten as t prime of t. The denominator ds over dt, that's the magnitude of r prime of t. The denominator ds over dt is the magnitude of r prime of t. Now, I try to make curvature and n here. I try to create curvature and n. What I can do is, if I multiply the top and the bottom by magnitude of t prime of t, if I multiply the top and the bottom by magnitude of t prime of t, this equation can be rewritten as magnitude t prime of t over magnitude of r prime of t times t prime of t over the magnitude of t prime of t. I switch the numerator like this. And by definition, this is the curvature of a curve. And this, by definition, this is n. This is vector n. The unit normal vector. The principal unit normal vector. This is the principal unit normal vector. So I prove dt over ds equal to curvature times n. Number 2, part B. Show that dB over ds is perpendicular to t. dB over ds can be rewritten as derivative of b with respect to s. By definition, the binomial vector b can be rewritten as t cross n. If I take derivative using product rule, I have dt over ds cross n plus t cross dn over ds. That's the product rule for cross product. Then by part A, dt over ds is curvature times n. dt over ds is the curvature times n. Observe here. Curvature is a scalar, n is a vector. A scalar times vector n is parallel to vector n. Cross product of two parallel vectors is always the zero vector. Cross product of two parallel vectors is always the zero vector. So dB over ds can be rewritten as the cross product t cross dn over ds. Now for cross product, this property says if vector a cross b equal to vector c, then a is perpendicular to c and b is also perpendicular to c. That's a property of cross product. If a cross b equal to c, it generates a vector. A cross b generates a vector that perpendicular to both a and b. Cross product a and b generates a vector that perpendicular to both a and b. So since dB over ds equal to the cross product of t cross dn over ds, that means dB over ds is perpendicular to t, and dB over ds is perpendicular to dn over ds. What we want is dB over ds perpendicular to t. So we have the conclusion. dB over ds is perpendicular to t. Number 2, part C. Let s squared plus 4y squared equal to 4 be an equation of a plane curve. At what point the curve has the largest curvature or least curvature? We are looking for the maximum of the curvature and the minimum of curvature. Let's first of all find the curvature first. The formula for curvature is magnitude of the cross product r prime of t cross r double prime of t over r magnitude of r prime of t cube. So first step, in order to use the formula, we need to first of all find a vector function for this equation. This equation only contains x and y. So if this is a plane curve, we assume this is a curve. This is a curve in the xy plane. So assume x squared plus 4y squared equal to 4 is a curve, represent a curve in the xy plane. In the xy plane, the z coordinate is always 0. So we assume z is 0. In the xy plane, we assume the z coordinate is 0. So z is 0. Next, we try to find a parametric equation for x and y. This equation can be rewritten as x squared plus 4y squared equal to 4. If I divide both sides by 4, it can be rewritten as s squared over 4 plus y squared equal to 1. Then it can be rewritten as s over 2 squared plus y squared equal to 1. If we try to match the equation cosine squared plus sine squared equal to 1, we have s over 2 equal to cosine t, y equal to sine t. Then if I solve an equation for x and y, I have s equal to 2 cosine t, y equal to sine t, z equal to 0. So the vector function can be written as r prime of t. The vector function r prime of t can be written as 2 cosine t, sine t, and 0. S component is 2 cosine t, y component is sine t, z component is 0. Then we take derivative. If we take derivative for r of t, I get r prime of t, which is negative 2 sine t, comma cosine t, comma 0. Derivative of cosine is negative sine, derivative of sine is cosine, derivative of 0 is 0. R double prime of t is negative 2 cosine t, negative sine t, and 0. Next, we compute the cross product for r prime of t and r double prime of t. Write I, j, k in the first row. R prime of t in the second row. R double prime of t in the third row. Then take cross product. I times determinant of cosine of t, 0, negative sine of t, 0, minus j times negative 2 sine t, 0, negative 2 cosine t, 0, plus k times negative 2 sine t, cosine t, negative 2 cosine t, negative sine t. Then take determinant for these 2 by 2 matrices. Cosine t times 0 is 0. Sine t times 0 is 0. Negative 2 sine t times 0 is 0. Negative 2 cosine t times 0 is 0. Negative 2 sine t times negative sine t is 2 sine square t. Minus double negative is positive. 2 cosine t times cosine t is 2 cosine square t. If we write it as in vector form, it's the vector 0, 0, 2 sine square t plus 2 cosine square t is 2. That's the cross product of r prime of t and r double prime of t. Next, we take a magnitude for the cross product of r prime of t and r double prime of t. We find the magnitude for r prime of t and r double prime of t. Using Pythagorean theorem, we get square root of 0 square plus 0 square plus 2 square, which is 2. That's the numerator of the curvature. Next, we try to compute the denominator of the curvature, which is r prime of t, magnitude of r prime of t. R prime of t is vector negative 2 sine t, cosine t, and 0. So its magnitude is square root of negative 2 sine t square plus cosine t square plus 0 square, which is square root of 4 sine square t plus cosine square t. This can be rewritten as square root of 3 sine square t plus sine square t plus cosine square t. I rewrite 4 sine square t as 3 sine square t plus sine square t. Then, if I add cosine square t and sine square t together, it becomes 1. So I have 3 sine square t plus 1. This is magnitude of r prime of t. The determinant of the curvature is magnitude of r prime of t cubed. So if I find the curvature can be written as magnitude of r prime of t cross r double prime of t over magnitude of r prime of t cubed. Which is 2 over square root of 3 sine square t plus 1 cube. That can be rewritten as, this can be rewritten as 2 times 3 sine square t plus 1 raised to negative 3 over 2. That's the curvature. In order to find the maximum and the minimum of the curvature, we need to take derivative. This is a single variable function. In order to find the maximum and minimum of the curvature, we use derivative test. So take derivative and find the critical points. Here we use chain rule to take derivative. K prime of t is negative 3 times 3 sine square t plus 1 raised to negative 5 over 2 times 6 sine t times cosine t. It can be rewritten as negative 18 sine t cosine t over 3 sine square t plus 1 raised to 5 over 2. If I use double angle formula for the numerator, negative 18 sine t cosine t can be rewritten as negative 9 times 2 sine t cosine t. Negative 18 sine t cosine t can be rewritten as negative 9 times 2 sine t cosine t. And 2 sine t cosine t, if we use double angle formula, 2 sine t cosine t is sine 2t. 2 sine t cosine t is sine 2t. Over the denominator, 3 sine square t plus 1 raised to 5 over 2. In order to find the critical point, we set both the numerator and denominator equal to 0. In order to find the critical point, we set both the numerator and denominator equal to 0. So next, we set the numerator equal to 0 and set the denominator equal to 0. Solve the equation for t. Let's solve the first equation. I can first of all divide both sides by 9. I get sine 2t equal to 0. Sine function occurs 0 when 2t is 0 plus minus pi plus minus 2 pi and so on. If I divide both sides by 2, t is 0 plus minus pi over 2 plus minus pi and so on. So the critical point here, critical point is 0 plus minus pi over 2 plus minus pi. Solve the other equation. I first of all raise both sides to the power of 2 over 5. Then here, 5 over 2 and 2 over 5 can cancel. We get 3 sine square t plus 1 equal to 0, which means sine square of t equal to negative 1/3. Sine square of t is a perfect square. Since perfect square cannot be negative, there's no solution for t. So there's no solutions. The critical point is 0 plus minus pi over 2 plus minus pi and so on. And since this curve x squared plus 4y squared equal to 4, if we use parametric equation, x equal to 2 sine t, y equal to sine t, it completes one cycle when t is from 0 to 2 pi. It completes one cycle when t is from 0 to 2 pi. So we only focus on t between 0 and 2 pi. We only focus on t is between 0 and 2 pi. So between 0 and 2 pi, t is 0 pi over 2 pi 3 pi over 2 pi. Next, we pick some test number to verify if the function is increasing or decreasing. Let's pick test number between 0 and pi over 2. I can pick pi over 4, that's a test number. And between pi over 2 and pi, I can pick 3 pi over 4. Between pi and 3 pi over 2, I can pick 5 pi over 4. Between 3 pi over 2 and 2 pi, I can pick 7 pi over 4. In order to testing for increase for maximum and minimum at 0, I pick test number before 0. Here I can use negative pi over 4. I can use a test number after 2 pi. Here I can pick 9 pi over 4. Let's test this number. Plugging each number into the derivative. Before we plug in, let's observe the denominator first. In the denominator, we have 3 sine squared t plus 1 raised to the power of 5 over 2. Sine square of t is always greater than or equal to 0. When we times 3, it's still greater than or equal to 0. And when we add 1, it becomes positive. A positive number raised to the power of 5 over 2 is always positive. Since the denominator is always positive, if the numerator is positive, k prime of t will be positive. But if the numerator is negative, k prime of t will be negative. So we only need to test for the numerator. If I plug in negative pi over 4, Negative pi over 4 times 2 is negative pi over 2. Sine negative pi over 2 is negative 1. Negative 9 times negative 1 is positive. If I plug in pi over 4 times 2 is pi over 2. Sine pi over 2 is 1. Negative 9 times positive 1 is negative. If I plug in 3 pi over 4, 3 pi over 4 times 2 is pi over 2. Sine 3 pi over 2. 3 pi over 4 times 2 is 3 pi over 2. Sine 3 pi over 2 is negative 1. Negative 9 times negative 1 is positive. If I plug in 5 pi over 4, 5 pi over 4 times 2 is 5 pi over 2. Sine 5 pi over 2 is the same as sine pi over 2, which is positive 1. Negative 9 times positive 1 is negative. If I plug in 7 pi over 4, 7 pi over 4 times 2 is 7 pi over 2. Sine 7 pi over 2 is the same as sine 3 pi over 2, which is negative 1. Negative 9 times negative 1 is positive. If I plug in 9 pi over 4, 9 pi over 4 times 2 is 9 pi over 2. Sine 9 pi over 2 is the same as sine pi over 2. Sine pi over 2 is 1. Negative 9 times 1 is negative 1. Negative 9 times negative 1 is negative. So, when t is this value, k prime of t is positive, negative, positive, negative, positive, negative. If the derivative is positive, the function is increasing. If the derivative is negative, function is decreasing. Increasing, decreasing, increasing, decreasing. So here we can see that when t equal to 0, pi, and 2 pi, there's a maximum. The curvature has a maximum. When t equal to pi over 2 and 3 pi over 2, the curvature has a minimum. So maximum curvature occurs when t is 0, pi, and 2 pi. Minimum curvature occurs when t is pi over 2 and 3 pi over 2. Next, let's plug in t into the parametric equation. Next, let's plug in t into the parametric equation and find the points. Parametric equation r of t is 2 cosine of t, sine of t, and 0. When t is 0, if I plug in 0 for t, cosine 0 is 1, sine 0 is 0. When t is pi, I plug in pi. Cosine pi is negative 1, sine pi is 0. When t is 2 pi, we get the same value when t is 0. When t is 2 pi, we get the same value as t is 0. So don't write the same point twice. When t is pi over 2, cosine pi over 2 is 0. Sine pi over 2 is 1. When t is 3 pi over 2, cosine 3 pi over 2 is also 0. Sine 3 pi over 2 is negative 1, 0. So in the xy plane, maximum curvature occurs at point 2, 0 and negative 2, 0. The minimum curvature occurs at point 0, 1 and 0, negative 1. Number 2, part D. let y equal to 1 over x with s greater than 0 be an equation of a plane curve. At what point the curve has the largest curvature? What happened to the curvature as s approaches to infinity? So in order to find the largest curvature, we need to compute the curvature first. For the function in the form of y equal to f of x, its curvature can be written as curvature of x is absolute value of f double prime of x over 1 plus f prime of x square raised to the power of 3 over 2. That's for a plane curve in the form of y equal to f of x. So here, f of x, in this problem, f of x is 1 over x, which can be rewritten as x raised to negative 1. F prime of x is negative 1 times x raised to negative 2, which is negative 1 over s squared. F double prime of x can be rewritten as 2x raised to negative 3, which is 2 over x to the power of 3. Then apply the formula. The curvature is absolute value of f double prime of x, which is 2 over s cubed over 1 plus f prime of x negative 1 over s squared raised to 3 over 2. That can be rewritten as 2 over s cubed 1 plus 1 over x to the power of 4 raised to 3 over 2. Let's simplify this function first. It looks too complicated. Let's make it a little easier. The denominator here is 1 plus 1 over x to the power of 4. The denominator is x to the power of 4 raised to 3 over 4. X to the power of 4 raised to 3 over 2, that's x to the power of 6. The denominator is x to the power of 4, and the power outside is 3 over 2. X to the power of 4 raised to 3 over 2 is x to the power of 6. So I can multiply x to the power of 6 to the top and the bottom. Multiply x to the power of 6 to the top and the bottom. On the top, I have 2 over s cubed times x to the power of 6. On the bottom, I have 1 plus 1 over x to the power of 4 raised to 3 over 2. And x to the power of 6 can be rewritten as x to the power of 4 raised to 3 over 2. So since they have the same power, I can multiply x to the power of 4 into the parentheses. I have x to the power of 4 plus 1 raised to 3 over 2. That's the denominator. The numerator is 2x to the power of 3. That's the simplified curvature. Next, in order to find the maximum curvature, we use derivative test. Let's take derivative first. K prime of x. Here we can use quotient rule. Derivative of the top times the bottom minus the top times derivative of the bottom. Then use chain rule times 4x to the power of 3 all over the bottom square, x to the power of 4 plus 1 raised to 6 over 2 over the bottom square. Next, let's simplify the top and the bottom. On the top, I have 6x squared x to the power of 4 plus 1 over 3 over 2. Leave the first term the same. Second term here, this 2 and 2 can cancel. S cubed times 3 times 4 times s cubed. I have 3 times 4 is 12. x cubed times s cubed is x to the power of 6. X to the power 4 plus 1 raised to 1 over 2 over x to the power 4 plus 1 raised to 6 over 2. On the numerator, I can try to factor. Here we can see that x to the power 4 plus 1 is a common factor. X to the power 4 plus 1 is a common factor. We pull out the lower power. Lower power is x to the power 4 plus 1 raised to half. So if I pull it out, x to the power 4 plus 1 raised to a half. If I pull out x to the power 4 plus 1 raised to a half, what's left here? In the first term, I have 6x squared left. X to the power 4 plus 1 raised to 3 over 4. If I pull out half, 3 over 2 minus half is 2 over 2, which is 1. X to the power 4 plus 1 raised to power 1 minus the second term, 12x to the power 6 stays the same. And I pull out x to the power 4 plus 1 to a half completely. What's left is 12x to the power of 6 over the denominator stays the same. X to the power 4 plus 1 raised to 6 over 2. Then I can cancel x to the power 4 plus 1 from top and the bottom. Since the bottom has larger power, use larger power minus smaller power. I have x to the power 4 plus 1 raised to 5 over 2. That's the denominator. On the numerator, this term gets cancelled. Then I can distribute. I have 6x to the power 6 plus 6x squared minus 12x to the power of 6. Then I can combine like terms. If I combine like term, I have 6x squared minus 6x to the power of 6 over x to the power 4 plus 5 over 2. Then I can factor. If I pull out 6x squared on the numerator, I have 1 minus x to the power 4 over x to the power 4 plus 1 raised to 5 over 2. In order to find the critical points, I set both the numerator and denominator equal to 0. So I set both the numerator and denominator equal to 0. Solve this equation here. I have 6s equal to 0, 6s squared equal to 0, and 1 minus s to the power 4 equal to 0. S equal to 0 and s equal to positive or negative 1, which means s equal to 1, s equal to negative 1. Since we only consider x greater than 0, so 0 will be rejected. Negative 1 will be rejected. The only critical point here is x equal to 1. Solve the other equation. I can raise both sides to the power of 2 over 5. Raise both sides to the power of 2 over 5. Then I have x to the power 4 plus 1 equal to 0, which means x to the power 4 equal to negative 1. Since x to the power 4 is always greater than or equal to 0, it cannot be negative 1, so there are no solutions here. The only critical point is s equal to 1. Then use number line test to verify if this is a maximum or minimum. Let's pick test number less than 1. Since we only consider x greater than 0, let's pick test number greater than 1. Less than 1, but greater than 0. I can pick x equal to half. And next, pick test number greater than 1. I can pick s equal to 2. If I plug in half and 2 into the derivative, if I plug in half and 2 into the derivative of a curvature, what do I have here? If I plug in half 6 times half squared is positive. Half to the power 4 is 1 over 16. 1 minus 1 over 16 is also positive. The denominator, s to the power 4 plus 1, is always positive. positive number times positive number divided by positive number is positive. If I plug in 2 into the derivative, 6 times 2 squared is positive. 2 to the power of 4 is 16. 1 minus 16 is negative. And on the denominator, 2 to the power of 4 plus 1 is always positive. Positive number raised to 5 over 2 is positive. So here, on the numerator, positive number times negative number is negative. Negative number over positive number is negative. So it's negative when s is greater than 1. Since the curvature, the derivative of the curvature is positive when s is between 0 and 1, the curvature is increasing between 0 and 1. And for x greater than 1, the curvature, the derivative of the curvature is negative. So the curvature is decreasing. Here we can see that curvature has a maximum when s equal to 1. The curvature has a maximum when s equal to 1. So maximum curvature occurs at s equal to 1. When s equal to 1, I can plug in 1 to find y. When s equal to 1, I can plug in 1 to find y. Y equal to 1 over x, which is also 1. So maximum curvature occurs at x equal to 1, y equal to 1, which means point 1, comma 1. So maximum curvature occurs at point 1, comma 1. Next, the second question in the problem asks, what happened to the curvature as s approaches to infinity? This is the curvature function. Here we'll take a limit as s approaches to infinity. So take a limit as s approaches to infinity. We have 2s cubed over s to the power 4 plus 1 raised to 3 over 2. If we plug infinity, we can see that the top is infinity, bottom is also infinity. In the case of infinity over infinity, we can apply L'Hopital's rule. In the case of infinity over infinity, we can apply L'Hopital's rule. If we apply L'Hopital's rule, take the derivative to the top and the bottom. On the top, I have 6x squared. On the bottom, use chain rule, I have 3 over 2 times s to the power 4 plus 1 raised to a half times 4x to the power of 3. If we simplify the top and the bottom, on the bottom, 3 over 2 times 4 is 6. 6 and 6 can cancel. So I have s to the power 4 plus 1 raised to a half. S to the power 2 and s to the power 3, if I cancel, there's x left on the bottom. Since both 6 and s squared can cancel on the top, there's a 1 left on the top. If I plug in infinity, the bottom is infinity. 1 over infinity is 0. So as s approaches to infinity, the curvature approaches to 0. As s approaches to infinity, the curvature of the curve approaches to 0. Number 3, part A. A baseball is hit 3 feet above the ground with an initial speed of 120 feet per second and an angle of 50 degrees with respect to the ground. What's the maximum height the ball can reach? How far does the ball travel in horizontal direction when it hits the ground? Based on what's given, a baseball is hit 3 feet above the ground. That means the vertical displacement is 3 when t is 0. And since the problem doesn't specify the horizontal displacement, we assume when t is 0, the horizontal displacement is 0. So when t is 0, horizontal displacement is 0. Vertical displacement is 3, since it's 3 feet above the ground. Vertical displacement is 3. Next, we know that the initial speed of the ball is 120 feet per second at an angle of 50 degrees with respect to ground. That means v0 is 120, initial speed is 120 feet per second, angle with respect to ground is 50 degrees. So the velocity when t is 0, the velocity at t is 0 is v0 cosine theta, v0 sine theta, which is 120 cosine 50 degree and 120 sine 50 degree. That's what's given. And we know that on the Earth, there's gravity that pulls objects downward. So the baseball has an acceleration g. G is a constant, which is 9.8 meter per second square, or 32 feet per second square. In this problem, since we use feet as unit, we use g equal to 32 feet per second square. So the acceleration of the ball horizontally, since there's no forces acting on the object, so there's no horizontal acceleration. Vertically, since there's gravity acting on the object has an acceleration 32 feet per second square. Since the gravity pulls objects downward, the vertical acceleration is negative 32. Next, we try to find the velocity based on the acceleration. Next, we try to find the velocity of the ball based on the acceleration. In order to find the velocity, we take antiderivative of the acceleration. Antiderivative of 0 is a constant. Antiderivative of negative 32 is negative 32t plus a different constant. Next, we try to find C1, C2. If I substitute 0 for t, I have C1, comma C2. Negative 32 times 0 is 0. By matching V0 here, we can see that C1 is 120 cosine 50, C2 is 120 sine 50. Then plug in. V of t is 120 cosine 50 degree, comma negative 32t plus 120 sine 50 degree. Next, we try to find the displacement of the ball. We try to find the displacement of the baseball. In order to find the displacement, we take another antiderivative. So for r of t, take antiderivative for the velocity. I have 120 cosine 50 times t plus a constant d1, negative 16t squared plus 120 sine 50 degree times t plus another constant d2. If I substitute 0 for t, r0 is d1. If I substitute 0 for t, first component is d1. Second component, if I substitute 0 for t, I get d2. And we know that r0 is 0, 3, 0, 3. So we know d1 is 0, d2 is 3. Plug in. R of t is 120 cosine 50 degree t plus 0, comma negative 160 t squared plus 120 sine 50 t plus d2. d2 is 3. That's the displacement of the baseball. Now let's look at the question here. What do they ask? The question is asking, what is the maximum height the ball can reach? When the ball reaches the maximum height, the vertical velocity must be 0. When the ball reaches the maximum height, its vertical velocity must be 0. So we set the vertical velocity equal to 0. Set the vertical velocity equal to 0. Solve for t. Then plug in t into the vertical displacement to find the height, to find the maximum height. So Set the vertical velocity equal to 0. Set negative 32t plus 120 sine 50 degree equal to 0. Solve for t. T is 120 sine 50 degree over 32. Use calculator, I get 2.8727. That means when t equal to 2.8727, the ball reached the maximum height. In order to find out what's the maximum height, I plug in t into the vertical displacement. So when t equal to 2.8727, the vertical displacement 16t plus 120 sine 50 degree t plus 3. Use my calculator. If I plug in t, use my calculator, I get 135.04. Rounding to the nearest whole number, I get 135 feet. That's the maximum height that the ball can reach. That's the maximum height that the ball can reach. Next question. We try to find out how far does the ball travel in horizontal direction when it hits the ground. How far does the ball travel in horizontal direction when it hits the ground? When the ball hits the ground, the vertical displacement must be 0. The vertical displacement must be 0. The height of the ball must be 0. When the ball reaches the ground, the vertical displacement must be 0, which means the height of the ball is 0. So we set the vertical displacement equal to 0, solve for t. Then plug in t into the horizontal displacement to find out how far does the ball traveled in horizontal direction. So I set the vertical displacement equal to 0 first. Set the vertical displacement equal to 0. Solve the equation for t. Here we can use quadratic formula. T equal to negative 120 sine 50 degree plus or minus square root of 120 sine 50 degrees squared minus 4 times negative 16 times 3. Negative b plus minus square root of b squared minus 4ac all over 2 times negative 16 all over 2a. That means 2 times negative 16. Then use my calculator, I get two solutions. T is negative 0.0325 and T is 5.7778. We know that in real life time cannot be negative, so this answer must be rejected. That means t must be 5.778. That means when t is 5.778, the ball reached the ground. When time is 5.7778 seconds, the ball reached the ground. So in order to find the horizontal displacement, we plug in t into the horizontal displacement. That's the distance the ball traveled. Plug in 5.778 into the horizontal displacement. That's how far the ball traveled. So when t equal to 5.7778, the horizontal displacement 120 cosine 50 degree t. I plug in t here and I use my calculator. I get 445.67. Rounding to the nearest whole number, I get 446 feet. So when the ball hits the ground, the horizontal displacement is 446 feet. Number 3, part B. A projectile is fired with an initial speed of 1000 feet per second and an angle of elevation of 30 degrees. If a 100-foot tall defensive wall is 5.1 miles away, will the projectile hit the wall? What is the speed of the projectile in impact? So when a projectile is fired, there are three cases. Either the range is too short, it doesn't reach the wall, or the range is too big, it flies over the wall, or it hit the wall. There are three cases. To determine which case, to determine whether the projectile will hit the wall, let's find the displacement function first. Let's find the displacement function for the projectile first. So what do we know so far? We know the initial speed is 1,000 feet per second with an angle of elevation of 30 degrees. So that means the initial velocity can be written as 1,000 cosine 30. Initial speed times the angle of elevation. Initial speed times cosine of the angle of elevation. And initial speed 1,000 times sine of 30 degrees. If I simplify, cosine 30 degrees is square root of 3 over 2. So it can be rewritten as 500 square root of 3. Sine 30 is half. That's 1,000 times half is 500. That's the initial velocity. Initial displacement. We assume this point, the location of this point is 0, 0. And what else do we know? We know on the Earth there's gravity pulling object downward. And when there's force added to an object, it generates an acceleration. When there's a force added to an object, it generates acceleration. Horizontally, there's no forces added to an object, but vertically, gravity is pulling object downward. So acceleration is 0, negative 32. Gravitational constant G is 9.8 meter per second square, or if 32 feet per second square. If we use instead of meter, it's 32 feet per second square. Since gravity pulling object downward, so we use negative 32. We use negative 32. And that's an acceleration for this projectile. Next, if we try to find velocity, you take antiderivative for the acceleration. Take antiderivative for 0. Antiderivative of 0 is a constant. It's called constant C1. Antiderivative of negative 32 is negative 32t plus another constant called C2. If I substitute 0 for t, I have C1 comma C2. I have C1 comma C2. Negative 32 times 0 is 0. Then by matching V0 here, I see that my C1 is 500 radical 3 and my C2 is 500. By matching the formula here, I see that my C1 is 500 radical 3, my C2 is 500. So V of t can be rewritten as 500 radical 3 comma negative 32t plus 500. Next, if I try to find the displacement, I take another antiderivative for V of t. R of t represents the displacement of an object. So in order to find R of t, I take another antiderivative for V of t. I get 500 radical 3 times t plus d1 comma negative 16t squared plus 500t plus d2. Then I substitute 0 for t. I try to find out what's d1, d2. I substitute 0 for t. If I substitute 0 for t, 500 radical 3 times 0 is 0. I get d1. If I substitute 0 for t, 16t squared plus 400t becomes 0. So I get d2 for the second component. By matching R0 here, we can see that my d1, d2 is 0, 0. So my d1, d2 is 0, 0. So the displacement is 500 radical 3 times t, comma, negative 16t squared plus 500 times t. We try to find out whether the projectile will hit the wall 5.1 miles away. Let's first of all calculate how many feet in 5.1 miles. So let's first of all multiply 5.1 miles equal to 5280. 1 mile is 5280 feet times 5.1. Use my calculator, I get 26,928. Next, I set my S component. I set my horizontal component equal to this number. I try to find out how long does it take the projectile to reach the wall. Next, I set my horizontal component equal to 26,928 feet. I try to find out how long does it take my projectile to reach the wall. So I set 500 radical 3t equal to 26,928. I divide both sides by 500 radical 3. I get my t is 31.09. My t is approximately 31.09. Once I find my t, next I try to find out what's the height of the projectile at when t is 31.09. When t is 31.09, I try to find out what's the height of my projectile. If the projectile is negative, means it doesn't reach the wall. If the projectile is over 100, it means it's gonna fly over. It's gonna fly over the wall. If the projectile is between 0 and if the height is between 0 and 100, that means projectile hit the wall. If the height is less than 0, means projectile doesn't reach the wall. If the height is more than 100, it will fly over the wall. But if the height is between 0 and 100, that means the projectile will eventually hit the wall. So I'm plugging t into the vertical component. I have the height of the projectile when t equal to 31.09 is negative 16 times 31.9 squared plus 500 times 31.09. Use my calculator, I get 77.72. If the height is between 0 and 100, that means it will hit the 100-foot tall wall. If the height is between 0 and 100, that means the projectile hit the wall. So, since the height of the projectile when t equal to 31.09 is between 0 and 100. The projectile hit the wall. The projectile will hit the wall. Next, we try to find out what is the speed of the projectile in impact. So, speed is the magnitude of the velocity. Speed is the magnitude of the velocity. Here, the velocity is 500 radical 3 comma negative 32t plus 500. So use Pythagorean theorem, find the magnitude. I have 500 radical 3 square plus negative 32t plus 500 square. Then for the speed at For the speed in impact, I plug in 31.09 for time. It takes 31.09 seconds for the projectile to reach the wall. So for the speed in impact, I plug in 31.09 for t. I get 500 radical 3 square plus negative 32 times 31.09 plus 500 square. Use my calculator, I get 997.51 feet per second. That's the speed in impact. I plug in 31.09 for t. Then I get 997.51 feet per second. That's the speed in impact. Number 4, part A. Limit as sy approaches to 0, 0, 2sy over 3x squared plus 4y squared. We try to use path test to show that the limit does not exist. So here, sy approaches to 0, 0. In order to use path test to show that the limit does not exist, we first of all plot point 0, 0 in the sy plane. In the sy plane, point 0, 0 is here. If we try to show that the limit does not exist, we try to show that the limit along two different paths that passing through 0, 0 has two different limits. In order to show that the limit does not exist, we need to show that limit passing through this point 0, 0 along two different paths is different. Let's try one path. Let's consider the y-axis. Y-axis is the path that s equal to 0. So along the path s equal to 0, which is the y-axis, this limit can be rewritten as along the path s equal to 0, this limit can be rewritten as 0y approach to 0, 0, 2 times 0 times y, 3 times 0 squared plus 4y squared. So this limit can be rewritten as limit y approach to 0, 0 over 4y squared. And we know that 0 over 4y squared is 0. Limit as y approaches to 0, the limit of 0 is 0. So along the path s equal to 0, the limit is 0. Next, let's consider a different path that passing through 0, 0. Let's think of different path. Consider this line. Let's consider this line, y equal to x. Let's consider the limit along this path, y equal to x. Along path y equal to x, This limit can be rewritten as s comma x approach to 0, 0. 2x times x over 3x squared plus 4x squared. So this limit can be rewritten as limit as s approach to 0, 2x squared over 7x squared. It can be rewritten as limit as s approach to 0, 2 over 7. The limit as s approach to 0, 2 over 7 is 2 over 7. So along the path y equal to x, the limit is 2 over 7. Since the limit along two different paths is different, this limit does not exist. So the limit does not exist. Number 4, part B. Limit as sy approach to 1, 1. S squared y minus 1 over sy squared minus 1. We try to use path test to show that this limit does not exist. In this limit, sy approach to the point 1, 1. Let's plot point 1, 1 first. Let's plot point 1, 1 in the sy plane first. Point 1, 1 is here. In order to use path test to show that this limit does not exist, we try to show that two different paths passing through this point 1, 1 has different limits. If two paths passing through this point has different limits, then the limit of this function does not exist. Let's think of one of the paths first. Consider this path. S equal to 1. This path is s equal to 1. Along the path s equal to 1, remember the path must go through this point. The path must go through the point 1, 1. So along the path s equal to 1, this limit can be rewritten as 1, y approach to 1, 1. 1 square y minus 1 over 1 y squared minus 1. This limit can be rewritten as limit y approach to 1, y minus 1 over y squared minus 1. Here I can factor the denominator. Y minus 1 over y plus 1 times y minus 1. Cancel y minus 1 from top and bottom. This limit can be rewritten as limit y approach to 1, 1 over y plus 1. If I substitute 1 for y, I have a half. So along the path s equal to 1, the limit is a half. Along the path s equal to 1, the limit is half. Next, let's try to take limit along a different path that passing through the point 1, 1. Consider this path here. Consider this path. Consider this horizontal line. This horizontal line is the path y equal to 1. Along the path y equal to 1, this limit can be rewritten as limit x, 1 approach to 1, 1. X squared times 1 minus 1 over x times 1 squared minus 1. So this limit can be rewritten as limit as s approach to 1, s squared minus 1 over s minus 1. If I factor the numerator, this limit can be rewritten as s plus 1 times s minus 1 over s minus 1. Cancel s minus 1 from top and bottom. This limit can be rewritten as limit s approach to 1, x plus 1. If I substitute 1 for x, I get 2. So along the path y equal to 1, limit is 2. Since along two different paths passing through the point 1, 1, we have two different limits. This limit does not exist. So limit does not exist. Number 4, part C. We try to use path test to show this limit does not exist. If the limit along two different paths passing through the point 2, -1 give you two different limits, then the limit does not exist. So let's choose two limits passing through the point 2, -1. Make sure the path you choose must go through the point 2, -1. 2, -1. S is 2, y is -1. We try to find a path going through this point 2, -1. Let's try some simple path first. First path, we can try the vertical line s equal to 2. So along the path s equal to 2, along the path s equal to 2, this limit can be rewritten as limit 2, y approach to 2, -1. I substitute 2 for each x. I have 2 plus y minus 1, 2 square plus y square plus 6y plus 1. This limit can be rewritten as y approach to -1. On the numerator, I get y plus 1. On the denominator, I have y squared plus 6y plus 5. I can factor, if I substitute -1, I get 0 over 0. I can try to factor the denominator. Denominator can be rewritten as y plus 5 over y plus 1. Cancel y plus 1. I have limit y approach to -1. over y minus y plus 5. Substitute -1, I have 1 over 4. So along the path s equal to 2, we get 1 over 4. You can try to take a limit along the path y equal to -1. Along the path y equal to -1, you have the limit x, -1 approach to 2, -1. Substitute -1 for each y. X plus -1 minus 1 over x squared plus -1 squared plus 6 times -1 plus 1. Substitute -1 for each y. Then this limit can be rewritten as limit x approach to 2 x over, sorry, numerator is x minus 2 over x squared, -1 squared is 1, 6 times -1 is -6, 1 plus -6 plus 1 is -4. Okay, I can factor the numerator, I can factor the denominator. I get x minus 2 over x plus 2 s minus 2. Take a limit s approach to 2, I have 1 over x plus 2, cancel s minus 2. If I substitute 2, I get 1 over 4, they are the same. If the limit along two different paths give you the same thing, it doesn't tell you anything, because there are infinitely many paths going through the point 2, -1. So next, we try to find a different path that goes through the point 2, -1. Try this path, y equal to 1 minus x. First of all, how do we know this path goes through the point 2, -1? You need to substitute the point to see if the point satisfies the equation. If the point satisfies the equation, that means this equation, this line, goes through the point. If this point doesn't satisfy like this equation, then this point, this path doesn't go through the point. So if I substitute 2 for x, 1 minus 2 is -1. So this point satisfies this equation, that means this path goes through the point. You can also draw the path. You can see that. If you draw this path, you can see that this path actually goes through the point 2, -1. So along the path y equal to 1 minus x, along the path y equal to 1 minus x, this limit can be rewritten as s comma 1 minus x approach to 2 comma -1. X plus 1 minus x minus 1 over x squared plus 1 minus x squared plus 6 times 1 minus x plus 1. So this limit can be rewritten as limit as approach to 2. On the numerator, x minus x can cancel. Positive 1, -1 together is 0. The denominator can be simplified as s squared plus 1 minus s squared. If you expand the perfect square, you get 1 minus 2x plus x squared. Distribute 6, you get 6 minus 6x plus 1. If we combine like terms, on the denominator, we get 2x squared minus ax 1 plus 6 plus 1 is a. The denominator is not always 0. But the numerator is always 0. So 0 over a non-zero constant is 0. This limit is 0. The denominator is not always 0. So 0 over everything is 0. So along two different paths, we get two different limits. So the limit does not exist. Limit does not exist by path test. Number 5, part A. Limit as syz approach to 1, 3, 5. 2x plus 3y plus 4z equal to 31. We try to use the epsilon delta definition to prove that this limit is 31. Epsilon delta definition says if this limit as syz approach to abc f of syz equal to L, then for all epsilon greater than 0, there is a delta greater than 0 such that for all points syz in the domain, if square root of s minus a squared, y minus b squared, z minus c squared is less than delta, then the absolute value of f of syz minus L must be less than epsilon. So let's use epsilon delta definition to prove this limit. First of all, assume square root of x minus 1 squared plus y minus 3 squared plus z minus 5 squared is less than delta. Next, we try to find out under what condition absolute value of f of syz minus L is less than epsilon. F of syz is the function 2x plus 3y plus 4z. That's f of syz minus the limit. The limit is 31. We try to find out under what condition this is less than epsilon. Then we try to find a value for delta that satisfies all necessary conditions to make this statement true. So start from here. We try to find out under what condition this expression is less than epsilon. This expression can be rewritten as (2x). If I plug in 1 for x, 2 times 1 is 2. If I plug in 3 for y, 3 times 3 is 9. Plus 4z. 31 take away 2, take away 9 is 20. 31 take away 2, take away 9. We have 20 left here. So this expression can be rewritten as 2x minus 2 plus 3y minus 9 plus 4z minus 20. Then using triangle inequality, this is less than, using triangle inequality, this expression is less than absolute value of 2x minus 2 plus absolute value of 3y minus 9 plus absolute value of 4z minus 20. If I factor 2 out, the first term can be written as 2 times s minus 1. If I factor 3 out, the second term can be written as 3 times y minus 3. If I factor 4 out, the third term can be rewritten as 4 times z minus 5. Then absolute value of x plus 1, s minus 1 can be rewritten as square root of s minus 1 squared. Absolute value of y minus 3 can be rewritten as square root of y minus 3 squared. Absolute value of z minus 5 can be rewritten as square root of z minus 5 squared. Next, we try to make each square root looks like this. So for the first square root, if I add y minus 3 squared and z minus 5 squared, this expression is larger than square root of x plus 1. For the second square root, if I add s minus 1 squared, leave y minus 3 squared the same, and add z minus 5 squared, this expression is larger than the expression here, y minus 3, since both terms here are positive. Third term, for the third square root, if I add x minus 1 squared plus y minus 3 squared and leave z minus 5 squared the same, this expression is larger than square root of z minus 5 squared because both terms here, x minus 1 squared, y minus 3 squared, they are non-negative. So this expression is larger than this. This expression is larger than y minus 3 squared. This expression is larger than s minus 1 squared. So the new expression here is larger than the original expression. If I combine like terms, this equal to 9 square root of s minus 1 squared plus y minus 3 squared plus z minus 5 squared. And since square root of x minus 1 squared plus y minus 3 squared plus z minus 5 squared is less than delta, so this expression is less than 9 delta. Since we try to make this expression less or equal to epsilon, so here we want (9 delta) to be less or equal to epsilon. So we can simply let delta equal to let delta less or equal to epsilon over 9. So if we let delta less or equal to epsilon over 9, this expression 9 delta will be less than epsilon. So under the condition delta less or equal to epsilon over 9, we can make absolute value of f of syg minus the limit less than epsilon. So let's make a conclusion. For all epsilon greater than 0, let delta equal to epsilon over 9. We need to pick a specific value for delta. There exists a delta. So pick specific value for delta. Let delta equal to epsilon over 9. If square root of s minus 1 square plus y minus 3 square, if s minus a square plus y minus b square plus c minus c square is less than delta. So here we have x minus 1 square plus y minus 3 square plus z minus 5 square is less than delta. If this square root is less than delta, then the absolute value of 2s plus 3y plus 4z minus 31 is less than epsilon. Let's complete the proof. Let's complete the epsilon delta proof. Number 5, part B. We try to use epsilon delta definition to show this limit equal to 3. Epsilon delta definition says, for all epsilon greater than 0, there is a delta greater than 0, such that for all points sy in the domain, if the distance between sy and AB is less than delta, then the absolute value of f of sy minus L is less than epsilon. So let's use epsilon delta definition to prove it. First of all, we assume square root of x minus 2 square plus y minus 3 square is less than delta. We try to find out under what condition f of sy minus L is less than epsilon. F of sy is square root of 2x plus y plus 2. The limit is 3. We try to find out under what condition this expression is less than the limit epsilon. We try to find out under what condition this is less than epsilon. Then we try to choose a delta that satisfies all necessary conditions. First of all, we try to find out under what condition this expression will be less than epsilon. Then next, we try to find a delta that satisfies all necessary conditions to make this statement true. So start from here. Let's simplify this expression first. How do we simplify this expression? What can we do here? When we see a square root, try to use conjugate first. I can write this as square root of 2x plus y plus 2 minus 3. Put it over 1. Then multiply the top and the bottom by the conjugate. 2x plus y plus 2 plus 3 over square root of 2x plus y plus 2 plus 3. Multiply by the conjugate. If I multiply the conjugate, the numerator can be rewritten as 2x plus y plus 2 minus 3. Denominator minus 9 here. 3 squared is 9. Denominator is square root of 2x plus y plus 2 plus 3. Since denominator is always positive, I can drop absolute value on the denominator. This square root is always positive. Plus 3 square root plus 3 is always positive. Since denominator is always positive, I can drop absolute value on the denominator. On the numerator, what should we do here on the numerator? How do I separate this? Here, x approach to 2, y approach to 3. If I substitute 2 for x, since x is approaching 2, y is approaching 3, if I substitute 2 for x, 2 times 2 is 4. So I can rewrite numerator as 2x minus 4 plus 4 plus y plus 2 minus 9 over denominator 2x plus y plus 2 plus 3. Simplify the second half. The first half I can pull out. Let's leave it for now. For the first half, 2x minus 4. Second half, if I combine like term, I have y minus 3 over square root of 2x plus y plus 2 plus 3. This can be rewrite as 1 over square root of 2x plus y plus 2 plus 3. If I use triangle inequality, this absolute value can be rewrite as absolute value of 2x minus 4 plus absolute value of y minus 3. If I use triangle inequality, then next, for the first term, I can pull out 2. I can pull out 2 from first absolute value. It can be rewrite as 1 over square root of 2x plus y plus 2 plus 3. Pull out 2, I can write it as 2 times x minus 2 plus y minus 3. Next, we try to find upper bound for this expression. We know that delta could be a very, very small number, but I don't know how small it is. Let's assume if delta is less or equal to 1, then if delta is less or equal to 1, then this expression is strictly less than 1. Then square root of x minus 2 squared plus y minus 3 squared is strictly less than 1. If the sum of two positive terms is less than 1, that means each term by itself must be less or equal to, but must be less than 1. So x minus 2 squared is less than 1, and y minus 3 squared is less than 1. If the sum of two positive terms is less than 1, that means each term itself must be less than 1. So absolute value of x minus 2 is less than 1. Absolute value of y minus 3 is less than 1. Absolute value of s minus 2 is less than 1. That means s minus 2 is between -1 and 1. Absolute value of y minus 3 is less than 1. Means y minus 3 is between -1 and 1. Let's simplify the first inequality first. If I add 2 to the middle, I need to add 2 to the left side and right side. So my x is between 1 and 3. For the other inequality, if I add 3 to the middle, I need to add 3 to the left side, add 3 to the right side. So y is between 2 and 4. Now let's try to use this relationship to find upper bound for this expression. Under square root, we have 2x plus y plus 2. Since x is between 1 and 3, so for 2x, I multiply all 3 parts by 2. 2x is between 2 and 6. 2x is between 2 and 6. Y is between 2 and 4. in the denominator, there's extra 2 here. We have 2x plus y plus 2. So I add 2 to the middle, add 2 to the left, add 2 to the right. If I add the middle together, 2x plus y plus 2 is between 6 and 12. Next, I take square root for this expression. Square root of 6 is less than square root of 2x plus y plus 2, less than square root of 12. To make it a little easier, square root of 6 is greater than 2. Square root of 12 is less than 4. So I can say square root of 2x plus y plus 2 is between 2 and 4. Next, observe the denominator. In the denominator, we have this square root plus number 3. So I need to add 3 to the middle, add 3 to the left, add 3 to the right. Add 3 to the middle, add 3 to the left, add 3 to the right. So I have square root of 2x plus y plus 2 plus 3 is between 5 and 7. That's the denominator. Next, I take reciprocal for all 3 of them. If I take reciprocal, 1 over square root of 2x plus y plus 2 plus 3 is between 1/5 and 1/7. And remember, when we take reciprocal, the larger denominator, the smaller it is. The smaller denominator, the larger it is. So the inequality sign changed. When we take reciprocal, inequality sign changed. So 1/5 is greater than the square root. That means this square root 2x plus y plus 2 plus 3, 1 over this expression is less than 1/5. So this expression is less than 1/5. To make it easier, we can say this is less than 1. To make it easier, this expression is less than 1. So if delta is less or equal to 1, we can prove that this expression here is less than 1, strictly less than 1. So if delta is less or equal to 1, this expression is strictly less than 1 times 2 times absolute value of x minus 2 plus absolute value of y minus 3. This should be 1. It can be rewritten as 2 times absolute value of s minus 2 plus absolute value of y minus 3. Absolute value of x minus 2 can be rewritten as square root of x minus 2 square. Absolute value of y minus 3 can be rewritten as square root of y minus 3 square. Then for the first term, if I add y plus 3 square, I'm making first term larger. For the second term, if I add x plus 2, x minus 2 square, I make second term larger. Then first term is larger than first term. Second term is larger than second term. Now they are like terms. Combined like term, I have 3 square root of s minus 2 square plus y minus 3 square. And this expression is less than, by our assumption, this expression is less than delta. So this is less than 3 delta. But we want to make 3 delta less or equal to epsilon. We want 3 delta less or equal to epsilon. So let delta less or equal to epsilon over 3, we can make this statement true. So as a conclusion, delta, in order to make this statement less than epsilon, delta must be less or equal to 1, delta must be less or equal to epsilon over 3. So let delta equal to the minimum of number 1 and epsilon over 3. Then delta will be less than both of them. Then let's make a conclusion. It's a conclusion. Say this. For all epsilon greater than 0, let delta equal to the minimum of 1 and epsilon over 3. Then if square root of x minus 2 square plus y minus 3 square is less than delta, then we know that delta is less or equal to 1, delta is less or equal to epsilon over 3, then the expression f of sy minus the limit will eventually be less than epsilon. So then the function square root of 2x plus y plus 2 minus the limit will eventually be less than epsilon. Let's complete the proof. Number 5, part C. Limit as xy approach to 0, 0. 2xy over square root of 3x squared plus 4y squared equal to 0. We try to use epsilon delta definition to show that this limit is 0. So we first of all assume square root of s minus a squared plus y minus b squared is less than delta. So square root of s minus 0 squared, which is s squared, plus y minus 0 squared, which is y squared, is less than delta. Assume square root of s squared plus y squared is less than delta. We try to find out under what condition the absolute value f of sy minus the limit is less than delta, is less than epsilon. So the function f of sy is 2sy over square root of 3s squared plus 4y squared minus the limit is 0. We try to find out under what condition this is less than epsilon. Then pick a value for delta that satisfies all necessary conditions to make this statement true. So start from here. We try to find out under what condition this absolute value is less than epsilon. So here, this expression can be rewritten as absolute value of 2sy over square root of 3x squared plus 4y squared. In the numerator, number 2 is always positive, so we don't need absolute value. X and y, it may be positive, may be negative. We must keep absolute value. On the denominator, square root is always positive, so we don't need absolute value. We can write it as square root of 3x squared plus 4y squared. Now, in the denominator, if I drop 3x squared, I have 2 absolute value of x times absolute value of y over square root of 4y squared. If I drop 3x squared, since this term is positive, if I drop a positive term on the denominator becomes smaller. When the numerator is the same, the smaller denominator, the larger it is. So this expression is larger than the original expression. If I drop 3x squared and make the denominator smaller, when the numerator is the same, the smaller denominator, the larger it is. So this expression is larger than this expression here. Then the denominator can be rewritten as 2 times absolute value of y. Square root of 4 is 2. Square root of y squared is absolute value of y. Next, I can cancel 2 from top and bottom and cancel absolute value of y from top and bottom. I have absolute value of x. Absolute value of x can be rewritten as square root of s squared. Square root of s squared, if I add y squared, the new expression is larger than the old expression, since y squared is always greater or equal to 0. If I add a non-negative term, I make the expression larger. So square root of s squared plus y squared is larger than square root of s squared. And we know that square root of s squared plus y squared is less than delta. So this expression is less than delta. We want to make delta less or equal to epsilon. So if I let delta less or equal to epsilon, I can make this absolute value less than epsilon. So by making delta less or equal to epsilon, I make this expression less than epsilon. Next, let's make a conclusion. For all epsilon greater than 0, let delta equal to epsilon, we must pick a value for delta. If square root of s squared plus y squared, if square root of x minus 0 squared plus y minus 0 squared is less than delta, this expression is equivalent to s squared plus y squared less than delta. So if x minus 0 squared plus y minus 0 squared is less than delta, then this absolute value here, 2sy over square root of 3s squared plus 4y squared minus 0. This absolute value is less than epsilon. Let's complete the epsilon delta proof. Number 5, part D. Use epsilon delta definition to show this limit equal to 3. So, first of all, assume square root of x minus 3 squared plus y minus negative 1 squared, which is the same as y plus 1 squared, is less than delta. F of sy is x squared plus 2sy minus the limit is 3. We try to find out under what condition this expression is less than epsilon. Then we try to find a delta that satisfies all necessary conditions to make this statement less than epsilon. Let's simplify this expression first. How do we simplify this expression? We know here x approach to 3, y approach to negative 1. If I substitute 3 for x squared, I have x squared minus, I get 9. So I write x squared plus minus 9 plus 9. The second term, if I plug in 3 for x, I have 6y. So I do minus 6y plus 6y. Leave minus 3 by itself. So if I plug in 3 for x, I have x squared become 9. So I write x minus 9 plus 9. If I plug in 3 for the second x, I have 6y. So I do minus 6y plus 6y. Then I group x squared minus 9 together. Group 2xy minus 6y together. What's left is What's left is 9 plus 6y minus 3 together is 6y plus 6. Then by triangle inequality, this is less or equal to x squared minus 9 plus absolute value of 2xy minus 6y plus 6y plus 6. For the first term, I can factor as x plus 3 times x minus 3. For the second term, I can pull out 2y. If I pull out 2y, it can be rewritten as x minus 3. For the third term, I can pull out 6. If I pull out 6, it can be rewritten as 6 times y plus 1. That's the simplified expression. Next, I try to find an upper bound for x plus 3, for 2y, for x plus 3, and for 2y. So we know delta is a very small number, but we don't know how small it is. So if delta is less or equal to 1, then this expression will be strictly less than 1, since it's strictly less than delta. So this expression, x minus 3 squared plus y plus 1 squared, is strictly less than 1. If the sum of two terms is less than 1, then each term by itself must be less than 1. So square root of s minus 3 squared is less than 1. Square root of y plus 1 squared is less than 1. Square cancel square root, so absolute value of x minus 3 is less than 1. Absolute value of y plus 1 is less than 1. So if absolute value of s minus 3 is less than 1, then s minus 3 is between -1 and 1. S3 to the middle, to the left side, to the right side. X is between 2 and 4. So absolute value of x is less than 4. Since absolute value of s plus 3 by triangle inequality is less or equal to absolute value of x plus 3 plus absolute value of 3 by triangle inequality. Absolute value of x is less than 4. Absolute value of 3 is 3. So x plus absolute value of x plus 3 is less than 7. For the other one, absolute value of y plus 1 is less than 1. Y plus 1 must be between -1 and 1. If I subtract 1 from the middle, from left side, from right side, I get y is between -2 and 0. So absolute value of y must be strictly less than 2. Since y is between -2 and 0, absolute value of y must be less than 2. So 2 times absolute value of y must be less than 4. So this expression is less than This expression is less than 7 times absolute value of s minus 3 plus 4 times x minus 3 plus 6 times y, absolute value of y plus 1. It can be rewritten as 11 times absolute value of x minus 3 plus 6 times absolute value of y plus 1. Absolute value of s minus 3 can be rewritten as square root of s minus 3 squared. Absolute value of y plus 1 can be rewritten as square root of y plus 1 squared. And try to match this term. make this expression looks the same. If I add a partial term here, I can make this larger. If I add a partial term here, this expression will be larger than the first term. If I add a partial term to the second part, this expression will be larger than the second term. That equal to 17 square root of x minus 3 square plus y plus 1 square. And we know this square root of s minus 3 square plus y plus 1 square, by our assumption, is less than delta. So this is less than 17 delta. We want 17 delta to be less or equal to epsilon. So we want we want 17 delta to be less or equal to epsilon. That means delta must be less or equal to epsilon over 17. So if I can make delta less or equal to 1 and delta less or equal to epsilon over 17, I can make this expression less than epsilon. So to complete the proof, let delta equal to the minimum of number 1 and epsilon over 17. So the conclusion. Conclusion. For all epsilon greater than 0, let delta be the minimum of 1 and epsilon over 17. Then if square root of x minus 3 square plus y plus 1 square is less than delta, then the absolute value of x squared plus 2sy minus 3 will be less than epsilon. Let's complete the epsilon delta proof. Number 6, part A. F of sy equal to sine of x squared y cubed plus 2x squared minus 3y. We try to find the first order partial derivative. So for f sub x of sy, we treat y as a constant, take derivative with respect to x. Treat y as a constant, take derivative with respect to x. So I have cosine of x squared y cubed, take derivative for sine, I get cosine. Then use chain rule times the derivative of the inside function. Since I treat y as a constant, I have 2x y cubed. That's the first term. For the second term, if I take derivative with respect to x, I get 4x. Since I treat y as a constant, the derivative of the third term is 0. So this can be rewritten as 2x y cubed cosine x squared y cubed plus 4x. That's f sub x. Next, for f sub y of sy, we treat s as a constant. Take derivative with respect to y. Derivative of sine is cosine. S squared y cubed, use chain rule. The inside stays the same. Then times the derivative of the inside function. Since I treat s as constant, I take derivative with respect to y. I get 3x squared y squared. Next, For the second term, since I take partial derivative with respect to y, I treat s as constant, so the second term becomes 0. For the third term, if I take derivative with respect to y, I get minus 3. This can be rewritten as 3x squared y squared cosine of s squared y cubed minus 3. That's f sub y. Number 6, part B. Find the first order partial derivative. This function has 3 variables. So for first order partial derivative, we must find f sub x, f sub y, and f sub z. For f sub x, we treat y and z as constant. So I treat this base as constant. Derivative of a to the power x is ln of a times a to the power x. So if I treat the base as constant, I use this rule here. I have ln of the base times y cosine z raised to 4x, then times the, by chain rule, times the derivative of exponent. I get 4 here. That's f sub x. For f sub y, I treat x and z as constant. So I use power rule, bring 4x to the front, power go down by 1. Keep the inside the same, use chain rule, times the derivative for the inside with respect to y. I get cosine z. Next, for f sub z, I take derivative with respect to z. I treat x, y as constant. So I bring 4x to the front, power go down by 1, it's power rule. Keep the parentheses the same, then use chain rule, times the derivative of the inside with respect to z. So I treat y as constant. Derivative of cosine is negative sign. Number 6, part C. Tension of xz squared plus y equal to ln of y plus z minus sy. We are looking for the first order partial derivative. This is an equation that contains x, y, and z. If we are looking for the first order partial derivative, we must treat z as a function of s and y. And we are looking for delta z over delta x and delta z over delta y. That's what we are looking for. Let's find delta z over delta x first. When we are looking for delta z over delta x, we treat x as a variable. In the equation, treat s as a variable, treat y as a constant, and treat z as a function of x. Then we take implicit differentiation here. So from left to right, take derivative for tension, I get secant square, use chain rule, the inside stays the same, xz squared plus y, and times the derivative of the inside function. When we have x times z squared, we need to use product rule, because z is a function of x, so we need to use product rule. Derivative of the first times the second plus the first times derivative of the second. When we take derivative for z, for function of z, we need to multiply by delta z over delta x. And the next second term is y. Since I treat y as a constant, derivative of y becomes 0. On the other side, ln of y plus z, I have 1 over y plus z, then use chain rule, times derivative for the inside function. Y becomes 0, z becomes 1. Then since we are doing implicit differentiation, I multiply by delta z over delta x. That's the second term here. For the last term, take derivative with respect to x. I get y. Since I treat y as a constant, I get y. Next, solve the equation for delta z over delta x. I can first of all distribute secant squared into the parentheses. I have z square secant square xz square plus y plus 2xz times secant square xz square plus y times delta z over delta x equal to 1 over y plus z times delta z over delta x minus y. Next, I try to move the term that contains delta z over delta x to the left side. So I have 2xz secant square xz square plus y delta z over delta x minus 1 over y plus z times delta z over delta x. Next, move this term over. I have negative z square secant square x z square plus y minus y. On the left side, I can factor pull out delta z over delta x. So delta z over delta x times 2xz times secant square xz square plus y minus 1 over y plus z. On the right side, I can pull out negative sign. Z square secant square xz square plus y minus plus y. Then divide both sides by this expression. I get delta z over delta x by itself. So delta z over delta x equal to negative z square secant square xz square plus y over 2xz times secant square xz square plus y minus 1 over y plus z. That's delta z over delta x. Next, we try to find delta z over delta y. For delta z over delta y, we take partial derivative with respect to y. That means I treat s as constant, treat y as a variable, treat z as a function of y. So take partial derivative with respect to y. I have secant square xz square plus y, use chain rule, times the derivative of the inside function. Take partial derivative with respect to y. Since I treat s as constant, constant stays the same. I treat z as a function of y, so take derivative for z square. I get 2xz times, this is implicit differentiation, times delta z over delta y, since z is a function of y, plus derivative of y is 1. On the other side, I have 1 over y plus z, use chain rule, times the derivative for y plus z. Derivative of y is 1. Derivative of z is delta z over delta y, since I treat z as a function of y, minus sy. Since s is a constant, I take derivative with respect to y. I get negative x. Next, we try to solve an equation for delta z over delta y. Solve an equation for delta z over delta y. I can first of all distribute secant square into the parentheses. I have 2xz times secant square xz square plus y plus secant square xz square plus y. On the other side, distribute 1 over y plus z into the parentheses. I get 1 over y plus z plus 1 over y plus z times delta z over delta y minus x. Next, I try to move the term that contains delta z over delta y to the left side. Sorry, here. The first term contains delta z over delta y. First term should be 2xc secant square xc squared plus y times delta z over delta y. Move the term that contains delta z over delta y to the left side. I have 2xc secant square xc squared plus y delta z over delta y minus 1 over y plus z times delta z over delta y. Move this term to the right side. It becomes negative secant square xz squared plus y plus y plus z minus x. On the left side, I can factor delta z over delta y out. I get delta z over delta y times 2xz secant square xz squared plus y minus 1 over y plus z. On the right side, I can pull out negative sign. I have secant square xz squared plus y minus 1 over y plus z plus x. Then I can divide both sides by this expression. So delta z over delta y equal to negative secant square xz squared plus y minus 1 over y plus z plus x over 2xz secant square xz squared plus y minus 1 over y plus z. Number 6, part D. Find the first order partial derivatives. If we mix s, y, z together as one equation, we treat z as a function of x and y. So to find the first order partial derivative, we must find delta z over delta x and delta z over delta y. When we are finding delta z over delta x, I treat x and z. I treat x as a variable, z as a function of x. I treat y as a constant. So here, take partial derivative with respect to x. On the left side here, use chain rule. Derivative of sine is cosine. Leave inside the same. And by chain rule, times derivative of the inside. I treat x as a variable. I treat z as a function of x. Y is constant. So use product rule. I treat x cubed y squared as one part. That's a function of x. Z is another function of x. Use product rule. Derivative of the first times the second plus the first plus the first times derivative of the second. On the other side, I take derivative with respect to x. X cubed becomes 3x squared, 2y squared becomes 0. 3z becomes 3 times delta z over delta x. Next, we solve an equation for delta z over delta x. So on the left side, distribute cosine into the parentheses. I have 3x squared y squared z times cosine of s cubed y squared z plus s cubed y squared times cosine s cubed y squared z times delta z over delta x. Leave the right side the same. Next, we can try to move delta z over delta x to the left side. everything else to the right side. So this expression can be rewritten as s cubed y squared cosine x cubed y squared z. Move 3 delta z dx over delta z delta over 3 delta z over delta x over. Move over. I have 3 times delta z over delta x. So keep this term on the left side. Move 3 delta z over delta x over. Then factor delta z over delta x out. Move this term over. On the right side, I have negative 3x squared y squared z cosine s cubed y squared z plus 3x squared. Then to get delta z over delta x together, I divide both sides by this expression. On the numerator, I can pull out negative sign. It can be rewritten as 3x squared y squared z cosine s cubed y squared z minus 3x squared over s cubed y squared cosine s cubed y squared z minus 3. It's delta z over delta x. Next, for delta z, delta y, I take partial derivative with respect to y. I treat x as constant. I treat y as a variable, treat z as a function of y. So take partial derivative with respect to y. On the left side, use chain rule. Derivative of sine is cosine. Leave the inside the same. Then use product rule for this expression. I treat the first part as a function of y. Z is also a function of y. Use product rule. Derivative of the first, 2s cubed y. Derivative of the first times the second plus the first times derivative of the second. Derivative of the second is delta z over delta y. On the other side, take derivative term by term. First term becomes 0. Second term is 4y. The last term is 3 times delta z over delta y. Then we need to solve the equation for delta z over delta y. First of all, we distribute cosine into the parentheses. We have cosine s cubed. If I distribute cosine, I have 2s cubed y. 2s cubed yz times cosine s cubed y squared z plus s cubed y squared cosine s cubed y squared z times delta z over delta y. Leave the right side the same. 4y plus 3 times delta z over delta y. Then move this term to the left side. Move this term to the right side. On the left side, I have s cubed y squared cosine s cubed y squared z. Move 3 delta z over delta y over. I have negative 3. Pull out delta z over delta y. Move this term over. Pull out delta z over delta y. Move from the first term to the right side. I have negative 2s cubed yz cosine s cubed y squared z minus plus 4y. Then divide both sides by this expression. I have delta z over delta y. The denominator is s cubed y squared cosine s cubed y squared z minus 3. on the numerator, I can pull out negative sign. Negative 2s cubed yz cosine s cubed y squared z plus 4y. So if I pull out negative sign, it should be minus 4y on the numerator. Number 7, part A. f of hy is 3x squared y to the power of 4 minus e to the power of sy. Find f sub xyy and f sub yxxx. Let's find f sub xyy first. So we first of all take partial derivative with respect to x. That means I treat y as a constant. Take derivative with respect to x. I get 6x y to the power of 4 minus y times e to the power of sy. Take partial derivative with respect to x. Next, find f sub sy. From f sub x, take partial derivative with respect to y. I have 24x y to the power of 3 minus, here we use product rule. Take partial derivative with respect to y, use product rule. Derivative of the first times the second plus the first times derivative of the second. Take partial derivative with respect to y. So f sub sy can be rewritten as 24xy cubed minus e sy minus sy e to the power of sy. This expression can be rewritten as 24sy cubed minus e to the power of sy times 1 plus sy. Next, take another partial derivative with respect to y. From here, take another partial derivative with respect to y. F sub xyy. Take another partial derivative with respect to y. I have 72xy squared minus, for the second term, use product rule again. Take partial derivative with respect to y. Derivative of the first times the second plus the first times derivative of the second. Take partial derivative with respect to y. I get x. And this expression can be rewritten as 72xy squared minus e to the power of sy times distribute x plus x squared y plus another x. That's 72xy squared minus e to the power of sy times 2x plus x squared y. That's f sub xyy. Next, we're looking for f sub yxxx. So I first of all take partial derivative with respect to y. For f sub y, I take partial derivative with respect to y. I have 12, start from here. I have 12x squared y to the power of 3 minus x times e to the power of sy. Then from here I take partial derivative with respect to x. Take partial derivative with respect to x. I have 24x y to the power of 3. Then here we need to use product rule. Derivative of the first times the second plus the first times derivative of the second with respect to y. Sorry, with respect to x. I have y times e to the power of sy. Then this can be rewritten as 24xy to the power of 3 minus e to the power of sy times 1 plus sy. Next, take another partial derivative with respect to x. f sub yxx. Take another partial derivative with respect to x. I have 24y to the power 3 minus, for the second term, use product rule. derivative of the first, y times e to the power of sy. Derivative of the first times the second plus the first times derivative of the second. Take partial derivative with respect to x. I get y. Then if I simplify, it can be rewrite as 25 y to the power 3. Factor e to the power sy out. I have y plus xy squared plus another y, which is 2y. 24y to the power 3 minus e to the power of sy times 2y plus xy squared. Next, take another partial derivative with respect to x. Take another partial derivative with respect to x. F sub y x x x. Take another partial derivative with respect to x. First term becomes 0. Since I treat y as a constant, first term becomes 0. Take partial derivative with respect to x. Here I use product rule. Derivative of the first times the second plus the first times derivative of the second. Take partial derivative with respect to x. I have first term become 0, second term become y squared. Then I can factor negative e to the power of sy out. Distribute y. I have 2y squared plus xy cubed. 2y squared plus sy cubed plus y squared. If I combine like term, I have negative e to the power of sy times 3y squared plus xy to the power of 3. Number 7, part B. Let f of syz equal to sine of syz. Find the mixed partial derivative f sub syz and f sub zyz. So the first one, f sub syz, you need to find f sub x first. Then take partial derivative for y, then take partial derivative for z. Let's find f sub x first. If I take partial derivative with respect to x, I treat yz as constant. I have sine, take derivative for sine, I get cosine. I have cosine of syz times yz. I can write it as yz times cosine of syz. Next, I take a partial derivative with respect to y. F sub sy. Take partial derivative with respect to y. I use product rule. Derivative of the first times the second plus the first times derivative of the second with respect to y. I have xz here. If I simplify this expression, it can be rewrite as z times cosine syz minus x y z squared sine of syz. Next, if I take partial derivative with respect to z, take partial derivative with respect to z, I need product rule from the first part, product rule from the second part. So do product rule from the first part, derivative of the first times the second plus the first times derivative of the second with respect to z, so I multiply by sy. Second part, take another product rule. Derivative of the first times the second plus the first times derivative of the second. Derivative of sine is cosine. Take partial derivative with respect to z, So I multiply by x and y. Then if I simplify, it can be rewrite as cosine of syz minus syz times sine of syz minus 2syz sine of syz minus x squared y squared z squared cosine of syz. It can be rewrite as 1 minus x squared y squared z squared cosine of syz minus 3 of xyz sine of syz. Next, we try to find f sub z y y z. For mixed partial derivative by Cross theorem, we can take it in different orders. I can write it as f sub y y z z. I can take partial derivative with respect to y twice, and then take partial derivative with respect to z twice. So let's find f sub y first. For f sub y, I take partial derivative with respect to y. I have sine, take derivative for sine, get cosine. I get cosine syz times xz. It can be rewrite as xz times cosine of syz. Take another partial derivative with respect to y. I treat sz as constant, so I get xz times negative sine xyz times partial derivative with respect to y, so I multiply by xz, which can be rewrite as negative x squared z squared sine of syz. Next, we try to take partial derivative with respect to z twice. F sub yyz. Take partial derivative with respect to z, I need product rule here. Derivative of the first times the second plus the first times derivative of the second with respect to z. I have x times y. So it can be rewrite as negative 2x squared z sine of syz minus s cubed y z squared cosine syz. Then for f sub yyz, I take partial derivative with respect to z, so do product rule twice. Derivative of the first times the second plus the first times derivative of the second. I'm taking the derivative with respect to z, so times sy. Now another product rule. Derivative of the first with respect to z, take partial derivative with respect to z. Derivative of the first times the second plus the first times derivative of the second. Derivative of cosine is negative sine. can take partial derivative with respect to z. Simplify. It can be rewritten as negative 2x squared sine of syz minus 2s cubed yz cosine syz minus 2s cubed yz cosine of syz plus x to the power 4 y squared z squared sine of syz. It can be finally be rewritten as x to the power 4 y squared z squared minus 2x squared sine of syz. Combine like term for these two terms, I get minus 4s cubed yz cosine of syz. Number A, part A. F of x comma y equal to sine of sy. Find the equation of the tangent plane at point pi comma 1/3. The equation of the tangent plane is z minus z0 equal to f sub x times x minus x0 plus f sub y times y minus y sub 0. Here, x0 is pi, y sub 0 is 1/3. For z sub 0, we plug in x0, y0 into the function, we can find z sub 0. That's f of pi comma 1/3. That's sine of pi times 1/3, which is pi over 3. Sine pi over 3 is radical 3 over 2. Next, we try to find f sub x and f sub y at point pi comma 3, pi comma 1/3. F sub x, if I take partial derivative with respect to x, I get cosine sy times y. If I plug in pi and 1/3, I have cosine of pi times 1/3 times 1/3. Cosine of pi over 3 is a half. Half times 1/3 is 1 over 6. For f sub y, I take partial derivative with respect to y. I get cosine of sy times x. If I plug in pi and 1/3, I have cosine of pi times 1/3 times pi. Cosine of pi over 3 is a half. Half times pi is pi over 2. Then use the formula for equation of tangent plane. I have z minus z0, which is radical 3 over 2. F sub x at pi comma 1/3 is 1 over 6. F sub x is 1 over 6. X minus x0, x0 is pi, plus f sub y. F sub y at pi and pi comma 1/3 is pi over 2. F sub y is pi over 2. Y minus y0. Y sub 0 is 1/3. Then simplify. Common denominator here is 6. I can multiply both sides by 6. If I multiply both sides by 6, I get 6z minus 3 radical 3 equal to x minus pi plus 3 pi times y minus 1/3. I get 6z minus 3 radical 3 equal to x minus pi plus 3 pi y minus pi. So if I move s, y, z to the same side, I have x plus 3 pi y minus 6z equal to 2 pi minus 3 radical 3. That's the equation of the tangent plane at point pi comma 1/3. Number 8. Find equation of the tangent plane at the point E, 0. Find the equation of the tangent plane at the point E, 0. That's the formula for equation of tangent plane. So E, 0 represent the point, the value of x0, y0. To find the z0, you plug in x0, y0 for x and y. I have E times ln of E plus 3 times 0. 3 times 0 is 0. E plus 0 is E. I get E times ln of E. ln of E is 1. E times 1 is E. So z0 is E. Next, I find the partial derivative with respect to x and y. Then plug in x0, e0, x0, y0 to evaluate f sub x and f sub y. For f sub x, I take partial derivative with respect to x. Here I need product rule. Derivative of the first times the second plus the first times derivative of the second. One over x plus 3y. Product rule, derivative of the first times the second plus the first times derivative of the second. Then evaluate at E, 0. Evaluate at E, 0. I have 1 times ln of E plus 0 plus E times 1 over E plus 0. ln of E is 1. E times 1 over E is also 1, which is 2. Next, I find f sub y. Take partial derivative with respect to y. I treat s as constant. So I get x times 1 over x plus 3y. Times 3. Then evaluate at E, 0. Plug in E for x, plug in 0 for y. I have E times 1 over E plus 0 times 3, which is 3. Then using the formula, z minus z0 equal to f sub x, which is 2. X minus x0, that's E, plus f sub y, which is 3, times y minus y0, that's y minus 0. Z minus E equal to 2x minus 2E plus 3y. That can be rewritten as 2x. That can be rewritten as 2x plus 3y minus z equal to E. I bring 2E to the left side, bring z to the right side. Number 9, part A. Let f of sy be x squared y cubed. Find the linear approximation at point 2, 1, and use it to estimate the value of f of 1.92, 1.05. The formula for linear approximation is L of s, y equal to f of a, b plus f sub x times x minus a plus f sub y times y minus b. Here, a comma b is 2 comma 1. So a is 2, b is 1. Let's first of all compute f of a, b. F of a comma b is f of 2 comma 1. I substitute 2 for x, substitute 1 for y. 2 squared times 1 cube. 2 squared times 1 cube is 4. Next, we try to find f sub x. F sub x, we take, for f sub x, take a partial derivative with respect to x. I get 2x y cube. At 2 comma 1, I plug in 2 for x, plug in 1 for y, which is 2 times 2 times 1 cube, which is 4. F sub y, we take a partial derivative with respect to y. That's 3x squared y squared. Then we substitute 2 for x, 1 for y. 3 times 2 squared times 1 squared, which is 12. Then use the formula for linear approximation. L of s comma y is f of ab is 4, plus f sub x is 4. X minus a is 2, plus f sub y is 12. Y minus b is 1. Next, we use the linear approximation to estimate the value of f of 1.92 comma 1.05. So for f of 1.92 comma 1.05, I plug in 1.92 for x, and I plug in 1.05 for y. I get 4 plus 4 times 1.92 minus 2 plus 12 times 1.05 minus 1. I get 4 plus 4 times negative 0.08 plus 12 times 0.05, which is 4 minus 0.32 plus 0.6, which is 4.28. Number 9, part B. Let z equal to f of sy equal to inverse tangent of s squared times y. If point s comma y move from 2 comma 0.25 to 1.996 comma 0.256, find dz and delta z. dz is the differential, and the formula for differential is delta z over delta x times dx plus delta z over delta y times dy. Delta z over delta x and delta z over delta y, they are partial derivatives. Dx is the change of x, dy is the change of y. Dx is the change of x. From 2 to 1.996, change of x is negative 0.004. dy is the change of y. From 0.25 to 0.256, change of y is 0.006. That's dx and dy. Next, let's compute the partial derivatives. Let's compute the partial derivative at the initial point, at the point 2 comma 0.25. Let's compute the partial derivative at the point 2 comma 0.25. Delta z over delta x. If I take partial derivative with respect to x, I get 1 over 1 plus x squared y squared times 2xy. If I substitute 2 comma 0.25, I have 1 over 1 plus 2 squared is 4. 4 times 0.25 is 1. 2 times 2 is 4. 4 times 0.25 is 1. I get half. So delta z over delta x at point 2 comma 0.25 is a half. Delta z over delta y If I take partial derivative with respect to y, I get 1 over 1 plus x squared y squared times x squared. Same thing, I plug in 2 comma 0.25 for x and y. I get 1 over 1 plus 1 squared times x is 2. 2 squared is 4. Half times 4 is 2. So the partial derivative at point 2 comma 0.25 is half and 2. Then plugging, I have one differential. dg is half times negative 0.004 plus 2 delta z over delta y is 2. dy is 0.006. Delta z over delta x is half. Delta z over delta y is 2. dx is negative 0.004. dy is positive 0.006. Plug in. Then I have half of negative 0.004 is negative 0.002. 2 times 0.006 is 0.012. Adding up, I get 0.01. That's dz. For delta z, we use final point, the value at the final point minus the value in the initial point. F of 1.996 comma 0.256 minus f of 2 comma 0.25. We use the value at the final point minus the value at the initial point, plugging the value into the original function, then subtract. Here I use my calculator. I get 0.00986. Number 9, part C. A circular sector is measured and the radius and the central angle are found to be 50 cm and 60 degrees respectively. If the possible error in measurement are 0.2 cm for the radius and 1 degree for the central angle, find the largest possible error and percentage error in the computation of an area. And that's the area formula, A equal to half of r squared theta. This function has two variables, f of r theta. This function has two variables, r and theta. What do we know about r and theta? In this problem, radius is 50 centimeter. Theta, central angle, is 60 degree. If I convert 60 degree to radian measure, it's pi over 3. The error in measuring the possible error for radius is 0.2. The possible error for radius is 0.2. And the possible error for central angle is 1 degree. We need to convert 1 degree to radian measure. When I convert 1 degree to radian measure, I take 1 degree multiplied by pi over 180 degree, which is pi over 180 radian. So convert 1 degree to radian measure, I get pi over 180. So that's the information, that's the given information. We try to use differential to estimate the error. So dA is f sub r times dr plus f sub theta times d theta. What's f sub r? If I take derivative with respect to r, I have r theta. F of r has two variables, r and theta. I have r theta. Take partial derivative with respect to r, I have r theta. R, radius is 50. Angle is pi over 3. If I multiply, I get 50 times pi over 3, which is 50 pi over 3. If I find f sub theta, take partial derivative with respect to theta, I get half of r squared. Plug in 50 comma pi over 3. I get half of 50 squared. That's 2500 over 2. Then plug in. The largest possible error is dA. dA is f sub r 50 pi over 3 times dr. dr is 0.2 plus f sub theta. It's 2500 over 2. 2500 over 2 is 1250 times d theta. d theta is pi over 180. If we simplify, I can cancel 0. Then this can be rewritten as 50 pi over 3 times 1/5 plus 125 pi over 18. 50 divided by 5 is 10. To make denominator the same, I multiply top and bottom by 6. I get 60 pi plus 125 pi. That's 185 pi over 18. It's dA. That's the largest possible error. Then now to find the largest possible percentage error. To find the largest possible percentage error, we use dA over A. We try to find dA over A. Let's find A first. Area is half of r squared theta. If I substitute 50 for r, substitute pi over 3 for theta, it can be rewritten as 1250 times pi over 3. That's 1250 pi over 3. So the largest percentage error it's dA over A. dA is 185 pi over 18. A is 1250 pi over 3. When we have fraction divided by fraction, keep the top the same, flip button over. 185 pi over 18 times 3 over 1250 pi. If we simplify, I get 2 and 7 over 15%, which is approximately 2.5%. Number 10, part A. Let z equal to e to the power of sy times tangent x. X equal to s squared plus st, and y equal to st cubed minus t squared. Find delta z over delta s and delta z over delta t, which means the partial derivative of z with respect to s and partial derivative of z with respect to t. Here, z is a function of x and y. Let's draw the tree diagram first. Z is a function of x and y. So z contains two variables, x and y. S is a function of s and t. X has two variables, s and t. Function x has two variables, s and t. Function y also have two variables, s and t. When we are looking for delta z over delta s, look at the tree diagram here. We have two branches of s, so that can be rewritten as delta f over delta x and times delta x over delta s. Another branch is delta f over delta y times delta y over delta s. Then let's take partial derivative and plug in. Delta f over delta x. If I take partial derivative with respect to x, I need to use product rule here. Derivative of the first times the second plus the first times derivative of the second. That's delta f over delta x times delta x over delta s. Take partial derivative with respect to s. We have 2s plus t plus delta f over delta y. Take partial derivative with respect to y. Since we treat s as constant, we don't need product rule here. So I get x e to the power of sy times tangent x times delta y over delta s. Take partial derivative with respect to s. We have t cubed. That's delta z over delta s. Next, we're looking for delta z over delta t. There are two branches of t here. So we have delta f over delta x times delta x over delta t. Another branch is delta f over delta y times delta y over delta t. Then take partial derivative and plug in. Delta f over delta x is the same thing. The same thing we have here. Y times e to the power of sy times tangent x plus e to the power of sy times secant square x times delta x over delta t. Take partial derivative of x with respect to t, I get s, plus delta f over delta y is the same thing. X e to the power of sy times tangent x times delta y over delta t. In function y, take partial derivative with respect to t. We have 3st squared minus 2t. So that's the answer. Number 10, part B. Let z equal to s cubed sine of ty squared, s equal to square root of t plus 1, y equal to cosine of xt squared. Find dz over dt. Here, function z has three variables, x, t, x, and y. X has only one variable, t. Y has two variables, x and t. Let's draw the tree diagram first. Z is a function of t, x, and y. T is the end of the branch. X is a function of t. Function y has two variables, x and t. And x is a function of t. Here we have four branches of t. We have, at the end of branch, we have four branches of t. So dz over dt can be written as delta f over delta t, that's the first branch. Second branch, delta f over delta x times dx over dt. Because x is a single variable function, so use standard d, ds over dt. Delta f over delta y times delta y over delta t plus the last branch, delta f over delta y times delta y over delta x times dx over dt. because x is a single variable function, so it's d with dx over dt. Then plug in delta f over delta t. If I take partial derivative with respect to t, I have s cubed cosine ty squared times y squared plus delta f over delta x. If I take partial derivative with respect to x, I have 3x squared sine ty squared times dx over dt. X can be written as t plus 1 raised to a half. So dx over dt can be rewritten as half of t plus 1 raised to negative half. That can be rewritten as 1 over 2 square root of t plus 1. So dx over dt is 1 over 2 square root of t plus 1 plus delta f over delta y. If I take partial derivative with respect to y, I have s cubed cosine ty squared times 2ty. That's delta f over delta y times delta y over delta t. Take partial derivative with respect to t. That's negative sine xt squared. Take partial derivative with respect to t. That's 2xt. That's the third term. The fourth term, delta f over delta y. Take partial derivative with respect to y. I get s cubed cosine ty squared times 2ty times delta y over delta x. Take partial derivative with respect to x. Take partial derivative with respect to x. I get t squared here times ds over dt. ds over dt is 1 over 2 square root of t plus 1. Number 10, part C. Let z equal to s to the power 4 y squared, s equal to t cubed plus 1, y equal to sine of t minus 1. Find dz over dt and d squared z over dt squared. Let's find dz over dt first. Here, z has two variables. So, z is the same as f. F has two variables, x and y. X is a function of t. Y is a function of t. So for dz over dt, we have two branches of t. First branch is delta f over delta x times dx over dt. Second branch is delta f over delta y times dy over dt. Then substitute delta f over delta x. If I take partial derivative with respect to x, I have 4s cubed y squared times dx over dt, that's 3t squared, plus delta f over delta y, that's 2x to the power 4y times dy over dt. Derivative of sine is cosine. It's cosine of t minus 1. It can be rewritten as 12t squared s cubed y squared plus 2x to the power 4y times cosine of t minus 1. Next, that's the first derivative. Now, next, we try to find the second derivative. So we take derivative again from here. This is a function of three variables. We have t, x, and y. This is a function of three variables. So dz over dt is the same as function g. Function g has three variables. t, x, and y. T is an independent variable, it doesn't go anywhere. X depends on t, y also depends on t. So to find the second derivative, d squared z dt, I take derivative for the first derivative. This function has three variables, t, s, y. T is an independent variable, s is a function of t, y is a function of t. To find the second derivative, we have three branches of t. First branch is delta g over delta t. Second branch is delta g over delta x times dx over dt. Third branch is delta g over delta y times dy over dt. Then plug in delta g over delta t. I take partial derivative with respect to t. I have 24t s cubed y squared. Take partial derivative with respect to t. Derivative of cosine is negative sign. So I get 2x to the power of 4y sine of t minus 1. That's the first one. Delta g over delta t. Plus the second one. Delta g over delta x. Take partial derivative with respect to x. I have 36 t squared x squared y squared plus a s cubed times y times cosine of t minus 1 times dx over dt. dx over dt, take partial derivative with respect to t. I get 3t squared plus delta g over delta y. Take partial derivative with respect to y. I have 24t squared s cubed y plus 2x to the power of 4 cosine t minus 1 times dy over dt. Take partial derivative with take derivative with respect to t. That's cosine of t minus 1.